I had the pleasure of working with Paul, but also with the whole group of his students and collaborators in the field and in the lab, and all of this made it a rich experience. And I must say, coming from the United States, I worked at the US Geological Survey at the time. We were so in love with the San Andreas, we really couldn't see any other fault at all. And Paul rid me of that focus, and we could see a larger world with more other faults. Okay. What's my answer to this question? Why do the largest continental earthquakes nucleate on branch faults? I will argue with Peter Bird that branch faults are the on-ramps to the transform superhighway. The transforms, due to their very large cumulative slip and high slip rates, have unique characteristics, and they rupture very, very far from failure. They have a very low friction. But to get these things going turns out to be very hard. And branch faults probably is the only way you get a big transform earthquake to begin. Okay, but first I have to convince you that branch faults are actually a thing and that they actually are nucleating these earthquakes. And then from there, to the extent that you are convinced, and you're entitled to your skepticism, then I'll show you how we explain this. So this work was triggered, as I think we were all kind of shocked to see, that the 2023 Kahramanmaraş earthquake nucleated on a little wannabe fault, a fault that had very low slip rate, didn't have the same sense of slip as the East Anatolian fault, a major transform. So how could that be? Is that just an aberration? And when we began to look at other events, we saw, no, it isn't. The Denali earthquake in 2002 ruptured on a branch fault, a thrust fault. And the Kokoshili earthquake ruptured on a branch fault, the Taeyang Lake fault. And the Wenchuan earthquake ruptured on some kind of branch, blind, some kind of connection to the main fault. And of course, Kaikoura ruptured on a branch fault as well. Now you might say, well, wait a minute. Everything in Kaikoura was a branch, almost, and there's some truth to that. But if we look at these 5 cases, and I'm using these 5 cases because until about the year 2000, we didn't have good enough data to locate the earthquakes on which these events began. Let me put the shoe on the other foot. None of these earthquakes ruptured on the long, straight part of these transform faults, including Kaikoura. There was 100 kilometers or so available. That's got to tell us something important about how these earthquakes begin. Okay, but it's a small data set, 5 earthquakes. So can we look at older earthquakes and get a sense of whether or not this is actually something that occurs widely? And I think with some hesitation, here is a case, the 1939 Erzincan earthquake, a magnitude 7.8, and based on fault mapping and its location and uncertainty, this earthquake probably ruptured on a branch fault off the North Anatolian. And if we look at the San Andreas, we of course don't know where the 1857 and 1906 earthquakes ruptured with any precision. But we can make this statement: there were plenty of branch faults available in the areas where these earthquakes probably nucleated. So at least we can't eliminate that possibility. We'll never be able to be sure about that possibility. Okay, but now this hypothesis runs into trouble. Because when we look at slightly smaller earthquakes, 7.7 and larger, we don't see it necessarily. So those are 2 earthquakes, including the 2023 event, where they clearly did not rupture on branches. And we have a couple of others, big ones, that probably didn't rupture on branch faults. So is that a problem with the data? Maybe. So there's 3 explanations. One is, as earthquakes get smaller, the epicenter is closer on this branch to the main fault, and it gets harder and harder to tell, given location uncertainties, whether or not it actually nucleated on a branch. Another possibility is that without a branch fault, the rupture fizzles out sooner, and you don't get up to 7.8 or 7.9. And of course, we always have to be on guard for this last explanation. We're over-interpreting too small a sample. But let's take a look at the Izmit earthquake, because it's well studied, and it's an interesting and ambiguous case. So you can see that the epicenter is 3-4 kilometers off the fault. So it's not impossible that it actually ruptured on a branch fault that is unmapped because it's in the basin there. But it's also possible that it ruptured on a dilatant jog on the fault, and a dilatant jog is unlikely to have a thick damage zone because this is not a structure that stays on the fault for very long. So which is it? We don't really know. And you might even say, well, now, wait a minute. Couldn't large transform earthquakes all rupture at bends and breaks and faults? Because that's where the damage zone is going to be thin. But there's a problem with that explanation, which is that if that's the case, they would have to rupture at very high stress levels, and the stress drop would be enormous, at least where it nucleated, and we never see that. The stress drops for big transform earthquakes are all extremely low. Now, another question we can ask is, okay, if branch faults, let's say magnitude 6 earthquakes, started these ruptures, do we see magnitude 6 earthquakes within, let's say, 10 or 15 kilometers of these transforms that did not trigger the transform? And the answer is we do. We see something like, this isn't advancing for some reason. Okay, here we go. So something like a quarter to half of the magnitude 6s that are close to a transform ruptured as a nucleation event. So depending on your point of view, you could say, boy, that's a really high number. Or you could say, well, wait a minute, at least half of them don't nucleate. So why would that be? Well, here's some possible explanations. The transform ruptured recently. It's an unfavorable geometry for the branch relative to the transform. Or it could have something to do with the velocity of rupture. Now, let's go look at the San Andreas, my favorite fault, and notice something really remarkable. These are the 3 largest transform earthquakes in California historically, and they're all seismicity holes today. Doesn't matter what magnitude you look, this is what you see. They're holes. And the simplest explanation, and I think the correct explanation, is it means they're nowhere near failure. And probably they never get near failure because they rupture at these very, very low levels of friction, and they never get up to failure. They have these unique characteristics. So this might mean that all transform faults rupture prematurely, and that you'll never see a lot of seismicity on transform faults before they rupture. There's no evidence that they're building up towards something. Okay, so how might the branch actually play a role in this? So let's think of the fault with this damage zone. And the damage zone is what makes these faults unique. It's a fluid saturated zone, and they have very, very low effective friction. In other words, the fault ruptures at very low friction. And evidence suggests that this is due to trap waves in the damage zone and flash heating of the pore fluids that can suddenly make these faults very, very weak if you can flash heat the fluids. Okay? And so this is kind of the behavior that we expect on transforms. They never get to static failure. They never behave like Byerly faults. You could call them Rice faults because they have these unique attributes. Okay, well, what does the branch fault do? The branch fault is a Byerly fault. It doesn't have a damage zone, and so it has the ability, it can only rupture when static failure is reached. So it has a much higher stress drop, and it can bang into the fault, cause this flash heating, and then propagate. So the branch fault, because it is a high stress rupture, can hit the transform really hard, heat up the water, and start these unique low friction behavior. So this is why our view is that branch faults are the on-ramps to the transform superhighway. Now, I mentioned earlier that super shear rupture may play a role here, and here's why it could. So in super shear rupture, the rupture is propagating faster than the waves, and so you end up with a Mach cone. A Mach cone is basically breaking the sound barrier in Earth. It happens all at once with a big bang. So imagine that you're at an angle to a transform fault, and a huge section of the transform fault all at once gets hit. So it's possible that this is another element that if you have a super shear rupture on a Byerlee type fault and you hit that transform fault really hard, you can trigger something that wouldn't have otherwise happened because the fault isn't about to fail. Now, here's the problem. The evidence for this isn't very good. So even for the 2023 earthquake, there's 2 papers that says it's super shear and 2 papers that says it isn't. And for all the other cases, the evidence just isn't clear. So we don't know that that's an important attribute, but it would make sense that it would. That if you can whack a transform over a large section of the fault and hit it really hard and get these fluids to heat, you have something going. Now, granted, we don't understand this whole phenomena, but this is actually already played out in the public eye twice, so we better figure it out. So last August, a high-angle reverse fault off the megathrust occurred in the region that the Japanese fear is the site of the next giant Nankai earthquake, and so they declared a megaquake advisory for a week, and it had very large consequences socially, because they're saying to people something could happen, and then they have this very difficult problem of when you cancel that warning, because you just have this feeling that the day you cancel it, the next day you'll have the earthquake. So you're playing with fire when you start taking these concepts and handing them over to the public. Now, the earthquake didn't happen, so all was more or less fine. And 8 years ago, this happened in California, when the Brawley seismic zone had a swarm, and the California Governor's Office of Emergency Services declared an earthquake advisory, also for a week, and it caused lots of shutdown of government buildings and things like that. So ready or not, the forces that be are thinking in these terms, so we need to understand how it works. And here's the last one, an interesting one. In December, we had a magnitude 7 on the Mendocino Fault. You could view the Mendocino Fault as a branch to the San Andreas. Aftershocks leaked onto the San Andreas that may or may not have been part of the 1906 rupture. So this looks like a case where another advisory could have been launched. For some reason, it wasn't. Okay, so here's our view. These branch faults may be how great continental earthquakes are born. If so, and I fully admit it's a big if, we've been looking in all the wrong places for where these big earthquakes begin. Thank you.